Today we're going to be presenting our talk, Alice in Kernel Land, Lessons Learned from the eBPF Rabbit Hole, with my colleagues Simon and JJ. My name is Valentina. I'm a vulnerability researcher at IBM X-Force Red, and I'll let...
Thank you. I'm Simon. I'm a cloud vulnerability researcher at Google. I met Valentina in 2020 while we were simultaneously doing research on eBPF. That's how we met.
And hi, my name is JJ. I work as a security researcher at Google as well. When I transferred to my new team at Google doing security research, I was looking for new projects to do, and I came across an article by Simon on eBPF. I started a project on that, and then later I found out Simon was joining my team. And now here we are.
So we're going to begin with a short introduction to eBPF and what it is. eBPF is a Linux kernel subsystem that was built as a refactor of classic BPF, which is Berkeley Packet Filtering, which was originally created to filter packets in the kernel. Now, modern eBPF serves as a technology that allows user mode applications to run code in the kernel without needing to load a kernel module. eBPF programs can be used to do all types of things, such as tracing, instrumentation, hooking system calls, debugging, capturing or filtering packets, of course, and even in recent times, we've seen it used to build rootkits. So what are the advantages of using eBPF? For one, developers don't need to know how to develop kernel code, which is a huge advantage. It's also easier than compiling and maintaining a custom modified kernel. eBPF programs are also easy to write. You can use a high-level language such as Python, Go, Rust, or C. And there's a lot of performance advantages to using eBPF. That's the main advantage to running directly in the kernel. It lends itself so that user mode applications can adopt an asynchronous programming style, which means fewer context switches from user mode to kernel mode, which is advantageous for modern hardware. As I stated before, eBPF programs can be written in a high-level language, such as C, Python, Go, Rust, and others. Then using a tool chain for your preferred programming language, the programs are compiled into eBPF bytecode. And here we have pictured some sample eBPF instructions, what they look like. So how does it work? Here we have a diagram of the eBPF ecosystem. So let's get into a brief overview. First, the user mode application loads the bytecode into the kernel via a syscall, and the eBPF verifier will perform checks on the bytecode. If the checks are passed, the bytecode is JIT compiled into the native instruction set for the architecture, or the instructions can be executed by the interpreter while running, just depends on the kernel configuration. Then the application attaches the loaded eBPF program into a hook point, and eBPF utilizes event-based execution, so the program will execute after it's triggered by some event that occurs at the hook point. Then the application can interact with the program via input and output with eBPF maps and helper functions. Whether unprivileged users can run eBPF programs depends on a syscontrol knob, which is called unprivileged BPF disabled. Unprivileged users are limited to where programs can hook, so the hook points that can be attached. In particular, unprivileged users are allowed to hook to a socket that the user owns. And in recent times, there's been kconfig, kernel configuration, config BPF unpriv default, which sets the syscontrol knob during runtime by default that restricts unprivileged users. That kernel kconfig has been set by default in popular distributions like Ubuntu, beginning around last year, 2022. And cap BPF is a Linux capability that can be granted to users or containers to run eBPF programs. There are also fewer restrictions on programs that can be loaded for a user that has cap BPF capabilities. So a little bit of a new development that happened recently. Unprivileged restrictions on eBPF programs are currently being revisited and discussed with the possibility that capabilities will be further restructured so that more users without cap sysadmin can run eBPF programs. And also, currently, eBPF has no LSM Linux security model hooks, so it's not protected by mandatory access control implementations like SE Linux for now. That may change in the near future. And therefore, eBPF security auditing still remains relevant and important. eBPF vulnerabilities pose a risk for applications that are given cap BPF capabilities or running in containers with the capability, even if unprivileged eBPF is not allowed. You may see this in actual environments for untrusted applications that process heavy I/O or networking activity. Some examples are services, firewalls, security or telemetry applications, and applications that run in containers that use eBPF. So a quick note on the threat model and attack surfaces that we are focusing on for this talk. Mainly, we're interested in vulnerabilities that allow privilege escalation, meaning going from unprivileged user to eBPF program to kernel execution to root. Theoretically, there are some attack surfaces that could lead to remote code execution in eBPF. For example, like in eBPF programs that do packet parsing operations or helper functions that assist with packet parsing. But this is not our focus. We're mainly focused on local privilege escalation for this talk. So there are 3 places where eBPF vulnerabilities can reside. It's either in the verifier, the JIT compiler, and the eBPF runtime, kernel runtime. When building a fuzzer, it's important to survey the types of vulnerabilities that can occur and how to detect them in order to automate corpus generation in a way that makes sense and gains the best coverage for the target. And on that note, we're going to review types of bug classes that can occur in each of these components to give context about what to keep in mind when building our fuzzer. The first component that we'll discuss is the eBPF verifier, which is the component at eBPF that ensures a program is safe to run in the kernel. It's one of, if not the most important component for security, because bugs there or undefined behavior there in this component have a direct effect on whether an unsafe program is allowed to run and what happens when it runs. One of the things that the verifier does to ensure safety is by keeping track of the expected values of scalar value registers that are used in an eBPF program. It imposes a restriction that only scalars can be added to pointers to access memory of shared maps. The verifier has to ensure that these scalar registers fall within the expected range and do not lead to out-of-bound memory accesses. Errors in how these ranges are calculated result in the ability to manipulate the verifier's checks and allow kernel memory corruption. Here's an example of a code snippet of an eBPF program that's written in Go that is accessing and updating a value inside the memory of an eBPF map. And the verifier must ensure that one of operations like this, the one that we show above, don't result in operating in out-of-bounds memory. An example of this kind of vulnerability is CVE 2020-27194, which was actually discovered by the first iteration of the fuzzer that we're presenting on today. It was caused by the miscalculation of 32-bit ranges, which were derived by 64-bit registers. This was actually a problem that was seen before the discovery of this bug, which prompted the eBPF devs to do individual tracking of 32-bit ranges separate from the 64-bit ranges. But unfortunately, the patch introduced another bug, which was found by our fuzzer. Another type of bug that can occur in the verifier is branching prediction bugs. The verifier must analyze all potential code paths of the program being loaded and ensure that the behavior at runtime falls within expected safe constraints that the verifier will impose. It patches out instructions that it believes will never be reached, or it also does not analyze branches it believes to be in a seen state already or technically safe. The reason for this is performance, as analysis on every single code path can grow exponentially. And bugs in the verifier's branching prediction mechanisms can lead to the ability to manipulate the program state to one that's unexpected by the verifier. An example of this type of bug is CVE 2023-2163, which was discovered by the second iteration of the fuzzer that we're presenting today, and will be discussed more in depth later. The last type of verifier vulnerability types of bug classes that we're going to discuss is just general logic bugs. So logic bugs can occur when traversing and verifying the program, but they're not directly related to the calculation of ranges. An example of this bug is CVE 2021-3490. This bug was caused by the verifier failing to update the bounds of scalar registers after 32-bit AND, or XOR operations. However, I want to emphasize that this was not an error in the calculation of the ranges themselves. And I think this is an important factor to keep in mind as we move on to discussing fuzzing later and ponder whether fuzzing scalar register operations is worthwhile if we think that the range calculation operations have already been exhausted and thoroughly audited. We'll quickly discuss where bugs may happen in the other two components I listed, starting with the JIT compiler. So the eBPF JIT compiler compiles the eBPF bytecode to assembly of the native architecture of the system. Again, one of the classes of bugs that might occur here are code generation bugs, but this is a broad category. But the example in this one is caused by optimization of code generation that leads to branching miscalculations. The CVE listed here is a vulnerability with how branch displacements were calculated for some architectures, which could cause the eBPF program to branch in an unexpected location in the program. This, of course, can violate the assumptions about the program state at the new jump target assumed by the verifier during static analysis. This will allow the possibility for an attacker using the new program state to get the program to do bad things that the verifier initially believed wasn't possible during runtime. This also highlights how architectural differences can manifest in eBPF. And a second type of bug class that can occur in the JIT compiler also falls into the code generation umbrella, but this one has to do with translation. So the CVE listed here is a bug in the way that classic eBPF programs are translated and compiled in the JIT compiler. One thing that I didn't mention previously is that eBPF still has support for classic BPF programs that use a slightly different instruction set. And the way that this is handled is by doing a translation from classic BPF to modern eBPF in the JIT compiler. And this highlights that legacy CBPF program support can also lead to issues. And lastly, I'm going to discuss vulnerabilities in the eBPF runtime component. eBPF has helper functions that can interact with the eBPF program during runtime. The code for this runs in the unsandboxed part of the kernel, which just means the normal part of the kernel code. And an example of a vulnerability here is CVE 2021-38166, which is an integer overflow and out-of-bounds write in the hash map lookup function. This vulnerability can be triggered if an application creates an eBPF map of a type hash map and calls a helper function within the eBPF program to retrieve a value stored in the map. A big portion of the eBPF runtime code attack surface is related to operating on shared maps and retrieving/storing their values. So what now? Automated vulnerability discovery. With proper context of the target, we began our automated vulnerability discovery process by targeting eBPF via fuzzing. After surveying the attack surface possible and potential for automated vulnerability discovery, the component we decided to target is the eBPF verifier. I'll hand it off to Simon.
Okay, thank you, Valentina, for the introduction to eBPF and the type of vulnerabilities that can occur. And there were a lot of details and a lot of very subtle vulnerabilities. So one of the reasons we decided to automate vulnerability discovery is at the time of making the slides, the verifier.c file alone has over 17,000 lines of code. And the code is very complex and complicated and it's difficult to read. So automating vulnerability discovery just makes sense to just make it easier for ourselves. And then the code is also very actively maintained. There's lots of changes. So one of the vulnerabilities we discovered, which was CVE 2020-27194, was introduced as a patch for another security issue, which contained, I think, hundreds, even thousands of lines of code. So eBPF is a standard, and if we can automate vulnerability discovery, we can likely port it to more than one implementation or more than one operating system or different versions of an operating system. So the approach we took was fuzzing, and some of the advantages of fuzzing are it doesn't require a very deep technical understanding of the verifier code itself. So we just know what the verifier expects. It expects eBPF programs. It can verify are secure. So we can just generate programs instead, and this is much easier than actually reading the verifier code and finding some of these more subtle logic issues. And the eBPF instruction set is not very large, which means we can generate all opcodes in a reasonable time frame when we implement the fuzzer and the input generation. And the eBPF interface, so the syscalls to load programs, to verify them, and then to actually execute them, it doesn't change much, meaning a fuzzer can be adapted relatively easy to various implementations as well. So at the time, we considered some existing solutions. This was in 2020, and there was an eBPF fuzzer for the Linux implementation. However, they were aiming at finding memory corruption issues in the verifier itself. So they would try to load a program that would cause, for example, an out-of-bounds read-write, and they did find issues. However, these are more the classical, if you will, memory corruption bugs. We were more interested in logic bugs that occur after the verifier has verified a program and made wrong assumptions about the program. Another alternative we considered was syscaller. It's a coverage guided and sophisticated kernel fuzzer. However, at the time, I was more interested in finding a singular issue, and I decided that it would be easier, instead of hacking on the syscaller Go source code, to just write an eBPF program from scratch, as it would take me around the same time. And syscaller is built to trigger and detect loud memory corruption issues, so your kernel panics, your AZEN, KZEN alerts, if you will. And we're interested in these like very subtle to find logic bug issues. So writing a fuzzer from scratch and tailoring it for eBPF allowed us to reap some advantages. For example, we can optimize the fuzzing input generator to generate valid eBPF programs, and then we can modify it quite easily for experiments. So for example, Valentina mentioned lots of different vulnerability classes. So if we believe, hey, maybe there's something fishy about this part of the code, we can optimize and bias the fuzzer towards these areas of the code. And we can also choose an appropriate architecture for the fuzzer. So usually, for example, with syscaller, you generate your input, you execute it, and then you repeat this in a loop. However, with eBPF, we need to verify programs, and not all programs we are going to generate are going to be valid, which means we can have one component generating programs, and then the other can fuzz the programs that are considered valid. So this allows us to build a more optimized architecture. And we can also implement a strategy for detecting bugs, because this is quite subtle, and I'll get into the details in the next slides. So the input generation, on a very high level, a naive fuzzer, will just throw random bytes at a program until it crashes. So the issue with this approach is that in order for a program to crash, well, or to trigger an issue in the verifier, we needed to pass the verifier first. So just having a naive bit flipping approach, even if it's coverage guided, just isn't optimized for performance in this case, because if we generate a long list, a long array of opcodes, they need to be correctly encoded, they need to specify a valid operation, specify valid registers, so source and destination, or they need to specify immediates that are inside of the allowed ranges. So that means if we generate eBPF programs and we have an input generator that's optimized towards this, we can just have a higher rate of programs that are considered valid by the eBPF verifier. So in the first version of the fuzzer, we generated programs by prepending a static program header that performed all necessary initialization. So when you load an eBPF program, some registers will point to, for example, the stack, or the network packet that is being filtered. And then we can set up an eBPF map that will be used during the program execution. So this part of the program always stayed the same. And after, we generated a variable length of an array of opcodes, mostly ALU operations. And then we just did random operations with random registers, random immediates in a random order. And then we would append a static program footer that exited the program cleanly. So we had this kind of skeleton approach where in the middle there was just a whole bunch of random operations. So this screenshot shows a loop which generates a number of instructions. And this variable is just dynamic. This depends. This is kind of a tunable. So you can say, I want to have between 10 and 20 instructions in each generated program. So the less instructions you have, the higher the probability is the program will be considered valid by the verifier, just because there's less places where something could go wrong. But if you have more instructions, then there's more complexity in the program, so there's a higher chance that something will go wrong. So we can see we're generating in this screenshot, in most cases with an 80% chance we generate an ALU operation. There are also other operations such as branching operations, but this fuzzer was naive compared to the second version and mostly just generated ALU operations. And the next screenshot shows the generation of an ALU operation where we just choose a random opcode such as addition or a multiplication. And then this continues on, or we choose a random source and destination register for the operation. And that's how the programs came to be. So now that we can generate eBPF programs, we have to consider error detection. So as Valentina mentioned, there's a lot of different vulnerability classes, some of them very subtle. For example, from the compilation of one program type to another, some that can occur after the verification. Some are just triggering a wrong assumption in the verifier where the verifier believes, okay, I have the correct range, but it's actually not the correct range. And these issues are likely hard to detect with the usual standards such as a kernel crash, just because an issue was triggered inside of the JIT code, in the resulting code, it doesn't mean it will actually crash the kernel. So in this version of the fuzzer, what we did is we relied on the fact that if you use pointer arithmetic, so you modify a pointer and then use it to access memory, for example, accessing a map, if the program passes the verifier, then the verifier is 100% certain that this pointer write will be inside of the bounds of the memory that it's writing to. So we can test this assumption by writing a magic value to the eBPF map at the end of the program execution. And then after the program executes, we can check if the magic value is inside of the expected range of memory. And if it's not, that means the value was written out of bounds. So this approach works. However, it's still not perfect. And we have an improved version of the error detection coming up. The problem with this is that the write could be in bounds, but it could still be outside of the expected range of the verifier. So let's talk about performance and scaling. So at the time, at least when I wrote the first version of the fuzzer, the eBPF verifier runs with a global lock, meaning that the fuzzer won't scale well. No matter how many CPUs you throw at it, it will always be bottlenecked by this lock. And this is bad news because we expect most of our time to be spent within the verifier. So this first version of the fuzzer generated less than 1% of valid programs, which means almost all of the computation time was spent in the verifier, which basically runs on a single CPU. So we have some architectural solutions for this. So at the time, I decided to extract the verifier code from the Linux kernel and compile it in user space. And this had several benefits for scalability. One was there were no context switches, so loading and verifying a program requires expensive syscalls, and we didn't have those. And we could kind of remove the logic of the verifier lock and emulate it, have multiple processes running at the same time. And it's also a lot easier to debug potential issues, just because you can just attach GDB to a user space program. You can compile it relatively quickly and add print statements and so on. So the downside is extracting kernel code and compiling it in user space. With the disclaimer, I didn't find a nice way of automating this. It's very time consuming and it's difficult to port just because there's so many dependencies you pull into the user space program, and there's a lot of low level code you have to emulate, like the kernel memory allocator and a lot of just low level kernel APIs that need to be either just no-opt or emulated in some way. So unfortunately, it was very difficult to adapt this approach to multiple versions. Just because the commit frequency of the eBPF verifier is quite high, so this makes this even more complicated. So this image also represents the architecture of the first version. So we have the eBPF in user space, which is called by the generator. And this emulates the kernel verifier, and it checks the program for safety and resets the emulation. And if the program is considered unsafe, we just generate a new program until the program is considered safe. And if the verifier believes this program is fine, there's no security issues here, we pass it on to the triager, which actually loads the program into kernel in a VM, and then starts fuzzing it, starts executing it with different random inputs. So it also tries to catch for the out-of-bounds bugs and reports them back to the main component of the fuzzer. So to summarize, the first version of the fuzzer, it was very scalable and fast to the user space fuzzing approach. However, it was hard to adapt this to new versions. So I think, summarizing, I think using kernel code in user space to fuzz a very specific part of code can be very fast and speed up the process, but it's very tedious and hard work until there is a really nice approach to emulate this nicely. So another pro was we had a first fuzzer that was just really optimized for eBPF input generation. So all the programs we generated were correctly encoded. However, there was no intelligent generation of programs. So it was just a list of opcodes, which is why the valid rate was less than 1%. And another pro was it was very easy to debug issues. And this fuzzer was written in 2020, and it was written in C++ and was never released. And then my colleague, JJ, will now tell you about the second version of the fuzzer.
Hello. It is a very funny thing that one of the first projects you take when joining a new team is based on a random article on the internet about eBPF fuzzing, and then you find out that the author of the article joins your team, helps you build this new project, and then you end up in Black Hat Asia in Singapore. So yes, in our previous strategy, the biggest issue was that only a fraction of the programs were considered valid. And what if we create a fuzzer that generates a high volume of syntactically valid programs? And we're looking for programs that are semantically wrong. What does this mean? Well, this means that the opcodes are encoded well, the jumps are also encoded well. It means that we have programs that look valid. But what we're hunting actually for is programs that look valid but invalidate the security rules that the eBPF verifier has. So we came up with this. It's a new fuzzer. Well, we started with a fuzzer, and we ended up with a fuzzing framework. Because we noticed that we had enough code to basically generate any type of eBPF programs easily. And we were like, OK, what if instead of like just throwing one type of like program generation, we create a way to generate multiple types of programs? And just like, what if people are able to create their own ways of generating eBPF programs and validating for issues in the verifier? And that's what we call like fuzzing strategies. And let's talk a little bit about what and why. And this all builds up on what Valentina already mentioned, that when you're building a fuzzer, it's very important for you to understand what type of issues you're looking for and how you detect when those issues happen. That's basically a fuzzing strategy. We build up a couple of fuzzing strategies. For example, the parse verifier log strategy, which we generate a bunch of random ALU operations. Then we parse the verifier's log to see what the assumption of the verifier were at verify time. And here, let's make an important note that there are basically 2 points in eBPF. One is the verify time, when the verifier checks that all the things that the program does are safe or adhere to the security rules. And then there is the execution time, when there are no more verifications, well, except for a few batch instructions. So at verify time, we get the log, and we parse the verifier's assumptions. At the runtime, we get the values of the registers, and we compare those values with those assumptions. If anything doesn't match, like, for example, like let's say the verifier thought like register 0 had value 1, but turned out the register 0 had value 2, then we flag this as a problem. Then there is the pointer arithmetic strategy, which is based on what Simon just presented. Basically, we generate a bunch of random operations on registers. This also includes some jump operations that we included later. And then at the very end of the program, we grab one of those registers and we add it to a pointer to a map value. And then we write to that pointer. At user space, then we check if at runtime, again, the value was actually written to the map. If the value is not there, then it means that very likely an out-of-bounds write happened. And this is the strategy that actually found the second CVE that we're presenting today, 2023-2163. I'm going to talk a little bit more about that in a little bit. Let's just dive in a little bit more in program generation. In a nutshell, our Foster's framework can generate programs in a tree-like structure, and there is an interface that people can grab and then implement their own Fostering strategies. There are other features, like we included coverage. We included also like some statistics. And for some statistics, it can generate around 35K eBPF programs per minute. For example, I've been running an instance of this Foster since last week, and I think right now we're around like 40 million programs generated, which is a pretty nice number. And again, like let me state very clear that a lot of those programs are going to be rejected by the verifier, and that's okay, because we are sure that the programs are being generated because being rejected because the verifier thinks it's an invalid pointer arithmetic. And that's more interesting than a program being rejected because only the encoding of an operation is wrong. And well, 24 hours after we set to run this thing for real, we got our first strike, 2023-2163. The TLDR, and thanks Valentina for the root cause analysis because it was very hard, is that the verifier, for optimization purposes, at any given point for branching, can decide, okay, I'm not going to follow this branch because I have already proven that in the state that I am currently at, if I follow this branch, I'm going to exit the program safely. There are other reasons why the verifier cuts branches, but this is the one that matters here. And turns out that the Foster found one of those cases where pruning a branch actually leads to an unsafe condition, and actually at runtime, it is this branch that gets followed, and well, it results in kernel read-write memory. So also another important thing of this bug is that we are very, very, very convinced that it will have been extremely hard to find by manual auditing, just because of how complex the verifier code is and just how complex the pruning logic is actually. And let's be real, like the verifier is actually trying to do a very hard job. Like proving that a program is safe, proving that a program reached a safe condition at the end, it's a very hard problem to do. So we actually turned this into a local privilege escalation plus container escape that I'm going to show you right now. So we are outside container in a syscaller VM. We have this folder that belongs to user. It's empty at first. Then we go to a container that runs with cap BPF. Just proving that we're inside a container and also proving that we are not able to read the user folder. So then we execute our exploit. It's going to take a while. So I can talk to you a little bit more what's going on here. Here we see that we leak some kernel memory addresses, and now we're trying to defeat ASLR by finding the init PID NS string offset. This is a common technique. You can go on the internet to read more on how to bound the kernel using this. Once we found it, we look for the process that is running inside the container. And we cannot rely only on the process ID because namespaces, so we look also for the executable name. Once we find it, we patch the credentials, and we patch we patch some other pointers, and then the file system pointer, sorry. And then we actually can read outside the container. So here we can see that actually the folder that was not available before, it's available now. We just write something to it for the purpose of demonstrations. We go back to our next shell, to our previous shell, and we see that there's a file there now. So, all right. So what now? Okay, so the coding of our Fuzzy framework name. Thank you. Thank you. Cool. The coding of our Fuzzy framework named Buzzer has been made open source. It's in github.com/google/Buzzer. There are still some features we want to implement, like executing eBPF programs in a distributed way across multiple VMs, across multiple versions of eBPF. I think there are some other operating systems also considering implementing eBPF. This is going to be very interesting. We will be interested in better metrics collection, more fuzzing strategies, etc. And we really just scratched the surface, because to find this CV, we literally only use arithmetic logic operations and jumps. And eBPF has so many other features, like helper functions. There are even loops. So, like, really, the future looks interesting here. And just to conclude with the sound bites that we were asked to add, like granting cap BPF for programs to run BPF, but to be able to load BPF, it still remains a complex attack surface. And we should be careful when deciding to grant this capability. When building a fuzzer, it's important to think what type of vulnerabilities I am hunting for, and how do I detect when these vulnerabilities happen. And there is a lot of value in the contribution between security researchers. Like, none of this will have happened just with a single researcher. Valentina did an amazing job with the root cause analysis. Like, we would have never understood that book without her. Simon, of course, did the first iteration of the fuzzer, which was the predecessor of the new fuzzer. And, well, now it's just a matter of, like, keep collaborating together, keep finding more bugs. And just to conclude, does anyone have any questions? Yes. Yes. The vulnerability happened by, OK, first, we generated programs that had arithmetic and logic operations and jumps, branching, all random operations. Then, after generating a certain number of operations, around like 500 maybe, we included a program footer where we loaded a eBPF map pointer that points to somewhere in user space, and we wrote to it. No, OK. First, we did an addition between a random register and this pointer. Then we try to write to that pointer. Usually what happens is the verifier will be like, you're insane, like this is not allowed. But we found just an edge case where this was not analyzed, so the verifier was not able to detect that this was insecure. And when writing to it, it was sent right out of bounds because the pointer was modified. So we didn't observe from user space that the write actually occurred. Any other questions?
In the slides, too, we can update it with the kernel commit that fixes the vulnerability that has, it's a pretty complex bug, so it'll explain everything that went wrong. It's kind of hard to describe in like a minute or two.
Yeah, actually, like if you go to my Twitter, is probably the tweet that I have pinned there, and like there is a link to the commit that fixes the bug. So if you want to go read how exactly it works, it's a nice write-up. Other questions? All right.
OK, well, thank you very much.
Thank you.